So dear students, in this lecture we will discuss the use of mesh analysis to determine the branch currents in a circuit in which we have a super mesh case. Now let us consider an electric circuit as shown in the diagram here. In this electric circuit we have to find out the current through each resistance which is connected here. In this electric circuit we have two voltage sources and one current source, right? So because in this two meshes, this one and this one, these two meshes share one current source in between, so it is difficult to apply the KVL in such type of network. So how to solve such type of network using mesh analysis, and how will we determine the current through the resistances as asked in this question? So let us see this particular numerical and try to understand the concept. The first thing that we do in such type of networks is we assume some voltage across this particular current source. So let us say this is a node A and this is B, this is node C for example, and this is node D for example. Okay, now we will assume some voltage across this current source. So let us say the voltage is Vx, right? So the voltage here is Vx, and rest of the things we will do in the similar manner as we did with the circuit where we did not have the super mesh case, right? So let us assume the circulating current in this mesh. So we'll assume it as clockwise, and this current is, let us say, I1. Similarly, the current in this mesh is again clockwise, and this current is, let us say, I2. And then we will take the currents in each branch here, right, like this. Now, this particular branch DAB is not shared by any other mesh. So this I1 current is assumed to be flowing in this particular branch. Similarly, the branch BCD is not shared by any other mesh. So the current I2, this one is, uh, you know, flowing in this particular branch BCD. So this is I2. Now we have two meshes here. We have two circulating currents, I1 and I2. Now we'll write the KVL equation. So KVL equation of mesh 1. So KVL equation of mesh 1 is, now let us write. So it is now like the direction of this voltage 10 volt is from minus to plus, and these two currents are matching, directions are matching. So we'll take it as plus 10. Then here the direction is matching, but we'll take this negative in case of resistance. So it is 10 I1, and now here the current is, from positive to negative. So this Vx will be taken as minus Vx. Okay, so this is minus Vx, so it is equal to 0. Now similarly, we will take the KVL equation of mesh 2, let us say, right? Now here you have the current I2 flowing in this branch, and this current and the direction of the circulating current is matching. So I'll write here minus sign is for the matching direction of the current in case of resistance, right? Minus I2 into 30. Then this same current is entering to the positive terminal of the battery and leaving from the negative terminal. So it is minus, and then uh, we have this. Now here the current, now this is the Vx is the voltage across this current source. So the current is from minus to plus, and we know that across a voltage, if the direction is, so the direction is from minus to plus, and this is matching here, so it will be taken as plus Vx and equal to 0. So let us say these are two equations. This is equation number 1 and this is equation number 2. Now in this case, because we do not have the you know uh, the resistance or resistive circuit or a voltage source here in the branch BD, and we do not know the voltage across this current source. So that is why we assume the voltage Vx across this current source. Now we will add these two equations. Now we'll add 1 and 2. Now by adding these two equations, what do we get? 10 minus 10 I1 minus Vx minus 30. Sorry, this is, I erase it. So it is minus 30 I2 and minus 8 plus Vx. This is plus is equal to 0, right? Now on simplifying this equation, we get equation number 3, which is 5I1 plus 15I2 is equal to 1. Now let us come back to the circuit diagram again. So in this circuit diagram, I'll remove everything from here as of now. So let us understand the concept here. So we took the voltage across this current source as Vx here, right? So this Vx is the voltage, no doubt. But if we apply some KCL at this particular junction, we were assuming that I1 is the current coming to this junction, I2 is the current leaving this particular junction. So this branch has I1 minus I2, means the net current, right? So that means we can write this current as in terms of I1 and I2. So now the current in branch BD is I1 minus I2 is equal to 0 0.3, right? So this is 0 0.3 ampere. So now we have two equations, equation number 3, and let us say this is equation number 4. Now we can solve these two equations because here also we have I1 and I2, and in this equation also we have I1 and I2, right? So we'll solve these two equations. So we can solve equation 3 and 4 to calculate I1 and I2, right? So what is the equation number 3? Equation number 3 is 5I1 plus 15I2 is equal to 1. So let's write it. 5I1 plus 15I2 is equal to 1. So let us see this equation once again. So it is divided by 2 here. So we have 5I1, 15I2 is equal to 1. Yes, correct. So that we have I1 minus I2 is equal to 0 0.3. So we can simplify, we can solve this equation. So let's multiply it here with 1 and here with 5 so that we can eliminate I1 here. So on doing so, we get, now we have solved this equation. On solving this equation, we have got uh, I2 is equal to minus 0.025 ampere. And now we can substitute this I2 in equation number 4, either in equation number 4 or in equation number 3, anyone, right? So we have got I1 is equal to 0.275 ampere, right? Now the negative sign indicates the actual flow direction of current. So let us see this. So that means actually the current in this I2 current is not flowing in this direction. It is actually flowing in this direction, right? So this is how the circuit works. If you find any circuit in which you have a current source being shared by two meshes, so you can solve that network in this manner. Thank you so much, guys.